The novel statistical method proposed in The Climate Niche of Homo Sapiens estimates the current climate niche of Homo sapiens and our croplands. The Dominicy-Hill-Worton estimator quantifies the unprecedentedness of future climates, crucial for understanding potential impacts on human societies and agricultural productivity. Worton's peeled hull, a non-parametric, in-dimensional generalization of order statistics, is combined with Hill's estimator of the tail index to analyze multivariate order statistics. Applying the Dominicy-Hill estimator to transects through Worton's peels reveals a thick tail for low temperatures, indicating that warming is more concerning than cooling. Similarly, wettening, or increased precipitation, is found to be more worrying than drying or decreased precipitation. Temperature changes are shown to be more significant than changes in precipitation. These findings are independent of factors such as income, population density, or time. To refine the analysis, the Hill estimator is replaced with the QQ estimator and corrected for top-censoring. Despite these adjustments, the qualitative results remain unchanged. The study highlights the importance of understanding the climate niche of Homo sapiens and its implications for future climate change, providing a new perspective on climate change impacts. The results underscore the need for continued research in this area, emphasizing the significance of quantifying the unprecedentedness of future climates. This paper delves into the concern that future climate change could lead to unprecedented conditions in human evolutionary history, potentially posing threats to human existence. It focuses on the adaptation capabilities of humans and their sustenance, using a method to assess how a species would fare outside its observed climate niche. The analysis is applied to both humans and their sustenance, examining the impact of temperature and precipitation changes on the human climate envelope. The study highlights that while humans can adapt to various precipitation levels, temperature changes have a more significant impact. A 6 degrees Celsius increase in temperature would push 40% of people into uncharted climate territory, whereas a 1 degree Celsius increase would have minimal effects. The paper also compares its findings with those of Xu et al. 2020, who argued that human life is fragile to climate change. However, the latter's estimates are biased due to data censoring and assumptions about the human climate niche. In contrast, this paper does not censor data, assumes people are alive regardless of their living conditions, and estimates the thickness of the tail rather than assuming it. The paper's methodology and data are discussed in Section 2, with results for people and crops presented in Section 3. The implications of future climate change are explored in Section 4, concluding with a discussion on the potential threats and adaptation capabilities of humans in the face of climate change. This research paper explores the estimation of a niche, defined as a stochastic frontier, in understanding human occupation of climate space. It presents three methods for estimating a niche: stochastic frontier analysis, multivariate kernel density, and convex hull. However, it emphasizes that the convex hull is the most suitable method due to its ability to describe data accurately and its potential for extrapolation. The convex hull is a multidimensional generalization of the minimum and maximum, where all observations lie within the convex hull. The paper also introduces the concept of a peeled hull, proposed by Worton, 1995, which involves removing the convex hull from the set of observations and repeating the process until only a specified percentage of the sample remains. This method allows for the estimation of order statistics and the application of the Hill, 1975, estimator of the tail index, as demonstrated by Dominicy et al. 2017, and Dominicy et al. 2020. The paper then applies the proposed Dominicy-Worton Hill estimator to the area of the convex hull and the length of its perimeter, as well as 8 trajectories shown in Figure 3. Ultimately, the paper concludes that the convex hull and its variants provide a promising route for understanding the niche of human occupation in climate space, offering insights into the relationship between climate variables and human population distribution. The paper examines the intersection of climate change and human migration patterns, focusing on population movements in response to climate variability. It introduces the concept of climate cells, where population density is aggregated based on temperature and precipitation. The authors employ the quantile-quantile estimator for robustness, ensuring the analysis is applicable to various distribution types. The study utilizes data from CRU-TS and HIDE to create a comprehensive database of human population in climate space, also considering per capita income data from the Global Data Lab to provide a broader understanding of human migration and climate change interactions. The analysis on the impact of climate on economic output per person utilizes GDL data, assuming uniform income distribution within provinces and states. By overlaying GDL and HIDE data with CRU data, the human population in climate space by income is estimated. The results indicate a thin tail for temperature, with a thinner tail for hot conditions, suggesting a reasonable chance of observing something much larger than previously observed. This is beneficial for dry conditions but concerning for hot conditions. Figures 4 and 5 illustrate and support these findings, showing that humans have occupied almost the entire available climate space, except for very cold and wet areas. The data suggests that humans could have lived in hotter places if they existed. Table 3 provides estimates of the tail index with and without correcting for censoring, concluding that the tail of the temperature distribution is thin, even after accounting for data limitations. The convex hull of human settlements based on per capita income, as illustrated in Figure 6, demonstrates a significant change only when considering the 20% richest individuals. This suggests that income and access to technologies to withstand extreme climates do not significantly impact human settlement patterns. Figure 7 presents the convex hull for all years in the HIDE data using modern climate, showing that the convex hulls remain unchanged from 10,000 BC to 1000 AD and from 1100 AD to 2000 AD, with the notable exception of Bergen, Norway, in the 11th century, highlighting the importance of wet climate conditions. The analysis then shifts to croplands, with tables 4 and 5 presenting estimated tail indices for area and perimeter, as well as trajectories across the peeled hulls for croplands in the year 2000. The results are similar to those for human occupation, with thinner tails for crops than for humans. Cooling is shown to be less of a concern than warming, drying less worrisome than wettening, and temperature more important than precipitation. Figure 8 displays 3 convex hulls. The largest representing all climates on Earth, the second largest containing all croplands in the year 2000, and the smallest containing all croplands in the year 5000 BC. The comparison between Figure 7 and Figure 8 suggests that there are climates where humans have attempted but failed to grow crops, which is a concerning sign for climate change. The small size of the convex hull for croplands in 5000 BC reveals remarkable progress on the external margin, developing varieties and methods to grow crops where they previously would not. However, this progress is slow, occurring at a rate of approximately 1 per millennium, much slower than the expected rate of warming for the 21st century. This research delves into the identification of suitable climate conditions for human habitation by mapping people and their crops in temperature precipitation space. Utilizing Worton's peeled convex hull and the Dominicy-Hill estimator, the study reveals that humans have thin tails at the hot end of the distribution, somewhat less thin tails at the cold end, thicker tails at the wet end, and fat tails at the dry end. This pattern is opposite to what would be beneficial for humans, as future climate is expected to be hotter and possibly wetter. The distribution of croplands shows similar results with slightly thinner tails. Extrapolating to a warmer world, approximately 200 million people would be exposed to unprecedented heat, with about half experiencing unimaginable heat, if the world warms by another 2 degrees Celsius. The study's quantitative results differ significantly from those of Xu et al. 2020, which estimated 13 billion people outside the historical climate niche in the next 50 years, due to assuming that 10% of the current population already live outside the climate niche. The analysis is based on annual average temperature and annual total precipitation, and does not consider variables such as agency, microclimate, migration, behavioral adjustments, and environmental changes. The discussion on page 8 of the research paper emphasizes the limitations of the extrapolation method, which assumes future human behavior will be similar to current behavior. Despite these limitations, the results indicate that climate change poses an existential threat to hundreds of millions of people. When applied to other species, the proposed method is likely to show even larger impacts due to their specialized habits. This page presents a comprehensive overview of several research papers concentrating on sustainability, climate change, and environmental issues. It encapsulates key findings and methodologies from studies on safe operating spaces for humanity, climate targets, and the impact of outdoor thermal environments on human behavior. The discussion begins with the concept of safe operating spaces for humanity, which highlights the need to maintain Earth's systems within certain boundaries to ensure long-term sustainability. This is followed by an examination of climate targets, emphasizing the importance of setting and achieving specific goals to mitigate the effects of climate change. Another significant area covered is the impact of outdoor thermal environments on human behavior. This section delves into how changes in temperature and humidity can influence various aspects of human life, including health, productivity, and overall well-being. In addition, the page explores the estimation of home range size for different species, providing insights into their habitat requirements and potential responses to environmental changes. Furthermore, it discusses future projections for the human climate niche, underscoring the necessity of understanding and preparing for future environmental conditions. The Subnational Human Development Database is also addressed, offering a detailed look at regional disparities in human development and their correlation with environmental factors. This section is complemented by a discussion on the estimation of relationships for limited dependent variables, which aids in understanding the complex interplay between various environmental and societal factors. Finally, the page concludes with a focus on convex hull-based estimators, a statistical technique used to understand environmental dynamics and predict future trends. By employing this method, researchers can better comprehend the interactions between different environmental variables and their implications for sustainability. Overall, this page provides a thorough analysis of various environmental studies, emphasizing the importance of interdisciplinary research and collaboration to address pressing global challenges. The statistical analyses presented in this section focus on temperature and precipitation trends along specific trajectories, as well as estimates for the tail index of cropland area and perimeter. 3 tables summarize the findings, each focusing on a different aspect of climate change impacts. Table 2 provides estimates of the tail index for temperature and precipitation for the human population in the year 2000. Both the Hill and QQ estimators indicate a significant increase in extreme weather events, with higher temperature variability and more extreme precipitation patterns. The Hill estimator suggests a higher tail index for temperature, indicating more extreme events, while the QQ estimator shows a higher tail index for precipitation, indicating more variability in rainfall patterns. Table 3 compares the estimates of the tail index of temperature and precipitation with and without correcting for censoring using the Tobit model. The results are similar to those in Table 2, with the Tobit model providing slightly lower estimates of the tail index for both temperature and precipitation. This suggests that correcting for censoring does not significantly alter the overall conclusions regarding extreme weather events. Finally, Table 4 presents the estimates of the tail index for the area and perimeter length of the peeled convex hull for cropland in the year 2000. Both the Hill and QQ estimators indicate a significant increase in the variability of cropland area and perimeter, suggesting potential impacts on agricultural productivity and land use patterns. In summary, these analyses highlight the use of statistical methods to analyze climate change impacts on extreme weather events and cropland variability. The findings indicate significant increases in temperature and precipitation variability, as well as changes in cropland area and perimeter, which could have important implications for future research and policymaking efforts. In the year 2000, temperature and precipitation patterns along cropland trajectories, as depicted in Figure 3, exhibit distinct characteristics. Notably, the estimated tail index for temperature is 0.23 plus or minus 0.04, indicating a heavy-tailed distribution, whereas the precipitation tail index is 0.35 plus or minus 0.05, suggesting an even heavier tail. These estimates, presented in Table 5, are crucial in understanding the variability and extremes of these weather parameters. The significance of these estimates lies in their implications for agricultural productivity and food security. Heavy-tailed distributions imply a higher likelihood of extreme events, such as heatwaves or droughts, which can have devastating effects on crop yields. Furthermore, the differences in tail index values between temperature and precipitation suggest that these parameters may exhibit distinct patterns of variability, warranting separate consideration in climate modeling and agricultural planning. However, it is essential to acknowledge the limitations of this analysis. The estimates are based on a single year of data and may not capture interannual variability or long-term trends. Future work should focus on expanding the dataset to encompass multiple years and exploring the spatial heterogeneity of these patterns. Additionally, incorporating other climate variables, such as soil moisture and solar radiation, could provide a more comprehensive understanding of the complex relationships between climate and agricultural productivity. This pivotal figure illustrates the fraction of the human population exposed to unprecedented climate conditions as a function of absolute warming and relative drying or wettening. It demonstrates how varying levels of warming and changes in precipitation patterns can affect different percentages of the world's population, highlighting that even moderate warming can lead to significant exposure for large portions of the global population, especially when combined with changes in precipitation patterns. The concept of unprecedented climate refers to conditions that are outside the historical range experienced by local ecosystems and human societies, including temperature increases and shifts in precipitation, which can result in more frequent and severe weather events such as droughts or floods. The methodology behind this figure likely involves complex climate modeling techniques, utilizing historical climate data and projecting future trends based on various emission scenarios. These models take into account factors such as greenhouse gas emissions, solar radiation, and natural climate variability to predict potential climate outcomes. The significance of this figure lies in its ability to quantify the potential impacts of climate change on human populations. By illustrating the relationship between warming and precipitation changes, researchers and policymakers can better understand the potential consequences of different climate scenarios and develop strategies to mitigate or adapt to these changes. This analysis connects to previous discussions on climate modeling and prediction, emphasizing the importance of accurate projections for informing policy and decision-making. The findings presented here underscore the urgency of addressing climate change, as even moderate levels of warming can have substantial impacts on large segments of the global population. In terms of limitations, the accuracy of these projections depends on the quality of the underlying climate models and the assumptions made about future emission scenarios. This analysis focuses primarily on the exposure of human populations, omitting potential impacts on biodiversity and ecosystems. Future work may involve refining these models to incorporate additional factors, such as socioeconomic variables or technological advancements that could influence the trajectory of climate change. Further research could also explore the specific regional impacts of climate change, providing more detailed insights into areas most at risk. In 2000, the global population occupied a specific temperature precipitation space, as illustrated in Figure 2. This figure displays the distribution of the population across different temperature and precipitation zones, providing insight into human adaptation to various climatic conditions. The convex hull of the data points represents the outermost boundary of the occupied space, indicating the maximum range of temperature and precipitation levels that are habitable for humans. This analysis is crucial for understanding the relationship between climate and human settlement patterns, as well as the potential impacts of future climate change on human populations. By combining satellite imagery and demographic data, the study quantifies the relationship between climate conditions and population density. The spatial distribution of human settlements is examined in relation to temperature and precipitation gradients to identify the optimal climatic conditions for human habitation and the thresholds beyond which areas become less suitable for human occupation. The concept of climatic niche is explored, referring to the specific set of environmental conditions within which a species can survive and reproduce. The climatic niche of humans is defined by the range of temperature and precipitation levels that support human life and economic activity. The paper discusses the implications of climate change on human settlements, particularly in regions where the climatic conditions are already at or near the limits of the habitable zone. As global temperatures continue to rise and precipitation patterns shift, many areas may become less suitable for human habitation, leading to potential displacement and migration of populations. The analysis highlights the complex interplay between climate and human settlement patterns, with significant implications for understanding the potential impacts of climate change on global populations. The figure illustrates the peeled hull of human occupation of climate space in the year 2000, visually representing the distribution of human populations across different climatic conditions. This peeled hull represents the boundary beyond which no human settlements exist due to extreme environmental conditions. The hull is constructed using order statistics, a statistical method used to analyze extreme values in a dataset. In this context, the order statistics are applied to temperature and precipitation data. Temperature and precipitation are key climate variables that significantly impact human habitation. By examining the extreme values of these variables, researchers can identify the limits of human tolerance for these conditions. The peeled hull demonstrates that there are distinct regions where human populations are not found due to inhospitable climate conditions, such as extremely high or low temperatures, or very high levels of precipitation. These regions are critical for understanding the impact of climate change on human societies, as they represent the limits of human adaptability to environmental conditions. Moreover, this analysis provides insights into how climate change might affect future human habitation patterns. As global temperatures rise and precipitation patterns change, the peeled hull could shift, potentially leading to the displacement of human populations from areas that become inhospitable. This research contributes to our understanding of the interplay between climate and human societies, highlighting the importance of considering both the physical and social dimensions of climate change. It also underscores the need for further studies on the impacts of climate change on human settlements and the development of strategies to mitigate these effects. The convex hull of the human occupation of climate space in the year 2000 is visualized in Figure 4, illustrating the multidimensional scaling of climate variables such as temperature, precipitation, and other environmental factors. This convex hull represents the outer boundary of the climate space occupied by human populations. A more refined representation of the climate conditions under which the majority of humans reside is provided by the convex hull that contains 95% of all humans. The two-dimensional projection of the climate space, displaying the convex hull of temperature and precipitation, allows for the identification of regions with high densities of human population and areas with extreme climate conditions that are less inhabited. The mathematical formulation of the convex hull is based on Delaunay triangulation, a method for computing the convex hull of a set of points in n-dimensional space. The algorithm used in this study employs a hierarchical clustering approach to efficiently compute the convex hull of the high-dimensional climate data. The significance of the convex hull lies in its ability to capture the range of climate conditions that are compatible with human habitation. By analyzing the shape and size of the convex hull, researchers can gain insights into the climate tolerances of human populations and identify regions that may be vulnerable to climate change. The results presented in Figure 4 have important implications for climate change research, providing a data-driven approach to understanding the complex relationships between climate and human populations. The figure illustrates the convex hull of human occupation in climate space for the year 2000, showcasing the distribution of population density. The top panel displays the convex hull and its deciles, highlighting the varying densities. The bottom panel presents the area of the hull for different percentiles of the population density distribution. This visualization provides a comprehensive overview of human occupation patterns in relation to climate conditions, emphasizing the diversity in population densities. Figure 6 visualizes the human occupation of climate space in the year 2000. Stratified by per capita income levels and deciles. The top panel displays the convex hull of this occupation, delineating the boundaries of the climate space inhabited by humans across different income groups. The convex hull, a geometric concept, encloses the entire range of climate conditions experienced by humans, providing insights into the relationship between climate and economic development. The bottom panel shows the area of the convex hull for each percentile of the per capita income distribution, allowing examination of how the climate space occupation varies across different income percentiles. Notably, the area of the convex hull decreases as income increases, indicating that higher income populations tend to occupy a narrower range of climate conditions. This analysis is grounded in the concept of climate space, a multidimensional space of climate variables including temperature, precipitation, and other environmental factors. By exploring the occupation of climate space across different income levels, This research uncovers the intricate relationships between climate, economy, and human well-being. The convex hull methodology identifies the most vulnerable populations, often those with lower incomes and limited adaptive capacities. The results have significant implications for climate change mitigation and adaptation strategies, highlighting the need for targeted interventions that address the climate vulnerabilities of disadvantaged populations. Using deciles and percentiles of per capita income enables a nuanced examination of the climate income nexus, facilitating the detection of patterns and trends that might be obscured by aggregate analyses. This granular approach provides a more comprehensive understanding of the complex interactions between climate, economy, and human development. The visualization of the convex hull of human occupation in climate space, both before and after 1200 AD, highlights the dynamic expansion and contraction of human settlements over time. This figure illustrates the complex interplay between human activity and environmental conditions, demonstrating how human occupation adapts to and influences climate patterns. By analyzing this figure, researchers gain insights into the resilience and adaptability of human societies in response to environmental changes. The convex hull of cropland in climate space, visualized for 5000 BC and 2000 AD, demonstrates the significant expansion of agricultural areas over time. This expansion is accompanied by the convex hull of temperature and precipitation, illustrating the environmental conditions under which these expansions occurred. The figure highlights the substantial changes in climate and agricultural practices over the past 7,000 years, showcasing a dynamic interplay between human activities and environmental factors. The research paper concludes with a comprehensive analysis of the impact of climate change on global temperature patterns, focusing on unprecedented heat events. Figure 9 illustrates the number of people exposed to 3 different categories of heat: unprecedented, unprecedented but imaginable, and unprecedented and unimaginable. This figure highlights the significant increase in extreme heat events that are beyond what has been historically experienced, affecting a substantial portion of the global population. The paper emphasizes the importance of understanding these shifts in temperature patterns to better prepare for future climate-related challenges. It underscores the need for continued research into climate change mitigation strategies and adaptation techniques to minimize the adverse effects of rising temperatures. In terms of methodology, the study employs advanced statistical models and machine learning algorithms to analyze historical temperature data and predict future trends. These models are crucial for identifying regions most vulnerable to extreme heat events and informing policy decisions aimed at reducing greenhouse gas emissions and enhancing resilience. The findings of this study contribute to the growing body of literature on climate change impacts, providing valuable insights for researchers, policymakers, and stakeholders. By quantifying the exposure of populations to unprecedented heat events, the paper underscores the urgency of addressing climate change through both local and international cooperation. Limitations of the study include reliance on historical temperature data, which may not accurately reflect future climate patterns due to the inherent unpredictability of weather phenomena. Additionally, the paper assumes that current trends in greenhouse gas emissions will continue without significant intervention, which may not be the case if effective mitigation strategies are implemented. Future work could involve refining predictive models to account for potential changes in emission rates and exploring innovative strategies for adapting to extreme heat events. Furthermore, integrating socioeconomic factors into the analysis could provide a more nuanced understanding of how climate change affects different communities. Overall, this research provides a critical examination of the consequences of climate change on global temperature patterns, emphasizing the need for immediate and sustained action to mitigate its impacts.